Yeah. Yes.
All right, so quick warm up here. I've got a guy who's looking in the mirror. The light bounces or starts at his feet. That's the object. It reflects off the mirror into his eye. And in order for him to see the top of his head, it needs to go from the top of his head to the mirror and into his eyes, right? So which ones are the angles of reflection? Notice they're labeled A, B, C, D, E, F, G, H. Identify the angles of reflection. There's two of them.
G and B.
So,
Oh, wait.
B is an incident ray.
Oh,
Right here, this is an incident ray.
because it goes
So
to the
between
eye.
the normal line and the incident ray is an angle of incidence. C.
Hold on. C
Between
and
the normal line and the reflected ray, and then what else? F. Right? Between the reflected ray.
she was like,
Oh yes, the any questions on 1 through 5?
Number 5.
Number 5. Whoa. So this really is a geometry problem, but optics are geometric. So here is a ray of light, and it's incident on this mirror, M1. And it shows us the angle of incidence is 70 degrees. So if the angle of incidence is 70 degrees, what do we know?
The angle of reflection.
Angle of reflection would also have to be 70 degrees. What do you know about the normal line? Perpendicular. So this whole thing has to be 90. So this angle, 20 degrees. How many degrees in a triangle?
180.
180. So I've got 140 here. So what is this one? 40. And here I have a right angle. So this angle of incidence is 50 degrees. So the angle of reflection, 50 degrees. So even though they don't look equal, I think probably that text box or graphics box got resized and it looks a little skewed, but it should be 50 degrees.
Okay, yeah, I think it was just the graphics that were confusing me.
All right, anything else on 1 through 5?
I was initially doing it right, but I just confused myself, so I ended up getting it wrong.
Catherine?
So the normal line is perpendicular to...
Always perpendicular. Perpendicular to the surface or perpendicular to the boundary between two media. Number 3, sure. So number 3 talks about Earth and Mars, and it gives you the distance from the sun to each of the planets. And then it asks you how much time it would take a radio signal to reach Earth from Mars. So the longest and shortest times. So if this is the sun, there's Mercury, Venus, Earth, and Mars. And so, but both of them are orbiting the sun, right? So, something like that. So, because they're going different distances and traveling at different speeds, sometimes they end up on the same side of the sun. So they're close together. That's actually known as the perihelion position. And at other times, Earth ends up on one side and Mars on the other. So the shortest time will be when they're close together. You know this distance from the Earth to the sun. You know this distance from Mars to the sun, and that would be the same here, even though it doesn't look like it in my sketch. So, shortest distance, or I'm sorry, shortest time, you will subtract these distances, and for the longest time for the signal to get from Mars to Earth, or whichever it was, you're going to add the distances. From here to here would be Earth to Sun plus Mars to Sun. And then it's just constant delta x equals vt. Anything else? So yesterday you did the refraction lab. We defined the normal line as the line perpendicular to the boundary between two media. We looked at angles of incidence formed between the normal line and the incident ray, angle of refraction that are between the refracted ray and the normal line. We will look at analyzing wave speed, frequency, and wavelength as the wave moves from the one medium to the other. On Monday, we defined and calculated index of refraction. Does anyone remember what's index of refraction?
Is that the ratio?
The ratio, right.
The speed
This
of
ratio?
light.
Yes. So index of refraction, N, is just a number that represents, or it's related to the optical density of the medium. So in substances that have a high optical density, the light travels slower. Like the mud, I think. Did I give you that example? It would be like if you were walking through water and you get going a certain speed, all of a sudden you start walking through mud, it has a higher density, you travel slower. It's the same type of thing with optical density, except it's light. And it travels a lot faster than us. So we'll be using that today. Remember the bending rules, faster away, slower toward? We'll be using those. And we'll solve some Snell's law problems. I noticed on the lab that most of you didn't answer the last question, so I think that would probably be a good place to start with that lab. So I think that's page 113. So I found some student work laying around, so I used the data that I found. All right. So normal line. So these measurements come from this ray diagram that I found. Angles, make sure your angles of incidence and refraction, any questions there? Briefly summarize the results. I just talked about how the light bent, right? So when the light went from the air into the glass, it bent toward the normal, and when it went from the glass into the air, it bent away from the normal. But it was this very last question here that most people skipped. So it says, using Snell's law, calculate the index of refraction for glass. So this equation that I had up yesterday is also on your equation sheet. Ni sine theta I equals Nr sine theta R is known as Snell's law. So using my data, unless you're going to use somebody else's data, this is the same as
Yeah.
That's why I don't use my. So here is one of the instances of refraction. Probably the first one is what it looks like, where it went from air into glass. So do we know the index of refraction for air?
Yeah.
1.
It's 1, right. So N here is equal to 1. We need to differentiate between the two indexes because we have two different mediums with two different indexes. So the medium where the light is incident, we're going to call that index Ni. Then the light gets refracted into the second medium. So since the second medium is where the light is refracted, I'm going to call that Nr. That's what we want to know. So we're given Ni equals 1. We measured the angle of incidence and the angle of refraction. Does anybody want to volunteer their data, or should we use this that I found? Go ahead.
I kind of forgot. Let me
Okay.
pull my sheet. Sorry.
So this angle right here
Uh-huh.
is the angle of incidence
Okay,
between the incident ray and the normal line, and this angle is the angle of refraction.
I have 35 for angle of incidence.
35 and
for refraction, that's 21.
21. That seems good. So what we want to calculate is the index of refraction for the glass. That's supposed to be a subscript. So I'm going to use Snell's law. I'll write it right here. Ni sine theta I equals Nr sine theta R. I want to solve for Nr, so I'm just going to divide by sine theta R on both sides. So Ni is 1. I'm going to substitute right here. So Nr equals Ni, which is 1, sine of the angle of incidence, which is 35 degrees, divide by sine of the angle of refraction, or sine 21 degrees. What does that come out to? First step is what?
Degree mode.
Degree mode.
Yep.
1.6.
1.6. The accepted value for crown glass is 1.52.
Okay.
Not bad. How we feel about that? Pretty easy?
Yeah.
As long as you're in degree mode. All right, so I have a couple of demos set up here. This is just a beaker full of water that has a pencil in it. And we had talked about this, how it looks bent because when the light rays enter the water, they slow down and change direction. So it kind of looks broken, right, where the surface of the water is. So example of refraction. How about this one?
Whoa.
So there's a glass stirring rod and that's just vegetable oil.
Wait,
So
is it still there?
it's still there.
I can kind of see. Huh?
So why do you think that the glass stirring rod seems to disappear? What properties would have to be the same? Yes.
Okay, so glass has the same refractive index as other glass, the glass on the outside, I'm assuming. So when you look at it, the light appears like going through the same light, but the oil is a different refractive index. Something related to that.
If it was a different refractive index, then it would bend, and we should be able to see it.
So they're the same.
So yes, so you were on the right track.
They blend in.
So it blends in because it just passes straight through and doesn't change direction.
Yeah, because they're the same index. But the oil is different, so the oil.
No, the oil is the same. Yeah, so because there's no change in direction, it seems to disappear.
So that oil has the same refractive index as the glass.
Or very similar, yes.
So if it had been water, then you'd still be able to see the glass.
I should do that. I'll bring that for you tomorrow. I'll get another graduated cylinder and bring it for you tomorrow. All right, so it's kind of fun though. And then this is cool too. So over here I have we call it a refraction tank. It has a little laser on it. I guess there it is. Okay, so this is just for demonstration purposes, but there you go. So here I have the light incident in the water. So this angle between the normal line and the incident ray, the angle of incidence, how does that compare to the angle of refraction? Bigger, smaller, same size? It's smaller. So does the light bend toward or away from the normal when it goes, right? So you can see that it's bending away. It's getting further away from the normal. The angle up here is greater, so it's further away from the normal than it is down here. So what do we know about the speed then?
It gets faster.
Faster in the air, right? Because we can see that it bends away from the normal. And then if I bring it up here, now the incident ray would be in the air, and the refracted ray, and I can't really see it, but it's maybe down here somewhere, and it bends which way?
Towards the normal line.
Towards the normal, yes. All right, so what's cool about this is notice down here, you see that there's a reflected ray as well? Oh, too much. Right here. So when the light is incident in the water, it's incident on this surface. Some of the light gets reflected back into the water, and some of it gets refracted. But if I increase that angle, because it's bending away from the normal, it keeps getting closer and closer to 90 degrees until all of the light gets reflected back in. So I'm increasing the angle of incidence until the light reflects back into the original medium. That is known as total internal reflection. And on page 115, there's a place for you to take notes on total internal reflection.
Is there a way to calculate the critical angle?
There sure is.
We ain't there yet.
We're going to use Snell's law for that.
Oh, of course.
Oh, I forgot about, I did have a couple of questions. All right. When light enters the block glass in the air, it slows down and changes direction. How does the frequency change?
It doesn't.
It doesn't change. What's the source of light that goes into the glass in this room?
The lights.
The overhead lights, right? So the source of the light is the same. It does, so it shouldn't change. The frequency shouldn't change as it moves from one medium to the other, right?
It just slows down.
So if the frequency of the light remains the same and velocity decreases, what happens to wavelength?
Decreases.
It also decreases, right? So there's a direct relationship between velocity and wavelength. Since frequency doesn't change, if velocity decreases, wavelength would also decrease. Right? So total internal reflection. It's really important, actually. I know you'll think it's important because it is the phenomenon that all of our fiber optic communication is based on. Is that, are fiber optic communication cables important to you?
Yes,
Yes.
very.
Yes, very important to you, right? Yes.
Not gonna lie, it gets very scary when you see like headlines and just like, this shark is eating fiber optic cables, and it's just like, that's
You're
definitely.
like, how am I gonna play video games with that lady in Germany?
How are you going to make long distance calls? Or do anything internationally? Like, if anything happened to those cables, like all of our international trade would just like halt.
Oh, so it's not all about video games?
No, it's also about
Oh.
like world order and
I was just teasing. Okay, so when light is incident in the more optically dense medium, so notice here the light was incident in the water. I don't get the same effect when the light is incident in the air, right? So if the light is traveling from the air into the water, it's just going to get closer and closer and closer to the normal until there's no change in direction at all, right? So I see a little bit of reflection right there, but I'm never seeing total reflection where all the light is reflected. So that's only going to happen when the light is incident in the more optically dense medium.
so it has to be in the same medium.
The light needs to be incident in the more optically dense medium, or where the light is traveling slower. So what happens is that light ray refracts closer and closer and closer to the boundary. So if right about almost right there, I'm getting an angle of refraction of about 90 degrees. If I exceed that angle of incidence, it all reflects back in. So right here, I just have a little bit, you can see just a glimmer that's still refracting, but it's refracting right along the surface. If I increase the angle of incidence just a little bit, then that doesn't happen anymore. So that is total internal reflection when all of the light reflects back into the original medium. So this is important, right? Only happens when the light is incident in the more optically dense medium, meaning that the first medium where the light is incident, Ni, has to be greater than the index of refraction where the light is refracted.
That makes sense.
Does that make sense?
Because it's like, that doesn't happen in air. Like it would always go through the water because it's.
Right, because it's just going to continue, as you increase the angle of incidence, it's just going to bend closer and closer and closer to the normal. Where when it goes from water into air, it bends away from the normal because it speeds up. So it approaches the boundary between the air and the water.
That makes sense.
So this is kind of what we just looked at, but in steps. So here is refraction, right? Bends away from the normal. When the angle of incidence is exactly equal to an angle known as the critical angle, then the light is refracted at 90 degrees. So this being the angle of refraction right here, 90 degrees. So every medium has its own critical angle. It's a property of that medium. So that critical angle is just the angle of incidence that produces angle of refraction equal to 90 degrees. Any angles of incidence greater than the critical angle, then we'll see total internal reflection. So the result is total internal reflection if the angle of incidence is greater than the critical angle.
What if the angle of incidence was 90 degrees, like parallel with the water at the exact angle?
So like this? Just goes
Yeah.
along the surface?
Yeah, so then it just like skids across. It doesn't go below or above.
Right.
Okay. It's interesting.
Yeah, that, I wanted to check, see if we saw anything different, but, we didn't break physics today. All right, so these are my shorthand notes, and so you can use this if you want. So TIR is total internal reflection. So it occurs when light is incident in the more optically dense medium and at an angle greater than the critical angle. So it needs to be incident in the more optically dense medium and incident at an angle greater than the critical angle. This is really what you need to solve for critical angle. So because we know that when the angle of incidence is equal to the critical angle, the angle of refraction equals 90 degrees, we can use that and Snell's law to solve for the critical angle. So I'll walk through that problem with you at the bottom of page 115. So suppose, is it water in the example? Oh, an unknown medium. So I'm just going to redraw basically what you have. So this is the N that is unknown. Up here is air. Do we know N for air? 1. All right. So if the light is incident in the unknown medium, is this Ni or Nr? Ni. The index of refraction where the light is incident. Right? And then air would be Nr. So if this angle of incidence, theta I, is equal to the critical angle, what's the angle of refraction? 90 degrees. So I'm going to label it here, theta R, 90, wow, that was unnecessary. Okay, so what do we know? We're given we're given Nr equals 1. We're given theta R equals 90 degrees, and it tells us the critical angle is 45. Theta C is 45 degrees. What we want to calculate is Ni. So Snell's law, Ni sine theta I equals Nr sine theta R. I'm solving for Ni, so I'm going to divide both sides by sine theta I. So Ni equals 1 sine 90 over sine 45, or 1 over sine 45. I think it's like 48 point, no, it's 1.5, we know the answer. 1
It's 2 over square root.
divided by sine 45, just make sure we get the right answer. 1.41. That's what it says the answer is, right? How do we feel about that?
Good.
So I have really another demonstration for you for this total internal reflection. So this is a, we call it a light pipe, but it's a piece of plastic, so it's solid, and it's got a curly Q in it, and it shows up a lot better if I turn off the light, so be warned. Hopefully I won't fall. So I've got a laser pointer here. Where is it? And I'm going to shine it into the end of this light pipe.
Oh,
So can you see that the end, right here in the middle of that curly Q, the end is illuminated? Do you see that? So that means that the light is traveling through the pipe around the curly Q. And if you're close enough, you can see the light reflecting off the surface of the plastic, right at the boundary between the plastic and the air, where it's incident in the more dense medium, the plastic. So that's how fiber optics work. All right.
if you just make different frequencies of waves.
Say again?
now, So if you just make different frequencies of waves do that, which aren't visible light, the ones that transmit like signals and stuff like that, then you effectively get intercontinental communication by carrying those waves across the pipe.
That's true.
Science! Physics!
Cool stuff. All right, so on page 114, you should see a diagram that shows light refracting through a block, similar to what you had in your lab yesterday. So now that we've talked about it, I would like you to practice in your groups calculating the index for that glass block. So I would like you to complete page 114 in your groups. If you have any questions, I'm happy to help.
I did this right.
Are we supposed to measure like?
Yeah, so that's why you needed the protractor when you came in.
So annoying because they're.
So make sure you draw your normal line.
Are you guys started on? Don't hit the camera, man.